Okay, on the last video, I shut it off prematurely. I meant to be zooming in and I hit stop, so the last video ended suddenly. That happens, and I'm too lazy to redo the whole video. So picking up where that last one went was where we picked up at, or last one where we left off. I was complaining that that was itty bitty tiny and I meant to zoom in and I hit the wrong button and I terminated the video. So picking up on this video and zooming in a little bit. I hit the right button eventually. There, we can see it now a little bit better, and now let's focus that. So that says log base 49 of 7. And so again, this is going to be the exponent needed to turn 49 into 7. Okay, a little harder, but not massively harder. I'm going to zoom out now. There we go. So you got to think 49 to what exponent gives you 7? And it's not obvious, not like the last one. Oh, yeah, 3. 2 cubed is 8. Remember, you can't, my exponents can be any number. When we talked about exponential functions, the domain of exponential functions was negative infinity to infinity, which means that exponents can be any number. So you're allowed to have 49 to any number. So I wish I had some students here in front of me. I don't, because generally I'd look at my class and I'd say, well, forget about exponents. How can you just in general turn 49 into 7? And eventually someone would say, square root. The square root of 49 is 7. So let's recall that the square root of 49 is 7. And then further recall that square roots and an exponent of 1/2 is the same thing as a square root. So this is 49 to the 1/2 equals 7. And so there's the exponent I need, 1/2. So log base 49 of 7 is 1/2. That you can use any number. So don't forget about square roots, cube roots, things like that. It's just that we have to change them to an exponent as opposed to a square root or cube root, as the case may be. Keeping that in mind, that you can use any number. And any number will include negative numbers. We get this next set of examples. And again, this is the exponent necessary, and let me remind you, or this is log base 10 of 1/10, and so this will be equal to the exponent needed to turn 10 into 1/10. And again, I would face the class, but there's not a class. Here is a room full of empty chairs. And I say, well, gosh, this is 10 over 1. I need to get that 10 in the denominator. What sort of exponents move things? And so we think back to when we reviewed exponents, and we said negative exponents. Negative exponents move things. And so then I would conclude, or I would write recall, that 10 to the negative 1 is 1/10. Negative exponents move things. And so log base 10 of 1/10 equals negative 1. That I can use negative exponents. Negative exponents move things. More of the same. So again, it's that 4, I got 4 and I got to change it to 1/64. So again, this is going to be the exponent needed to turn 4 into 1/64. Let's concentrate first on the 64. And so let's recall, or let's say let's note. How about note? 4 cubed is 64. 4 times 4 is 16, times another 4, 64. But 64 isn't quite what I want. I want 1/64. So 4 to the negative 3, which is 1 over 4 cubed, is 1/64. And there's my exponent. There's the exponent I need. I need negative 3. So log base 4, excuse me, of 64 is negative 3. Okay, next one. Log base 112 equals 1. 112 is sort of a weird number, but that's okay. Again, still exponent needed to turn 112 into 1. Again, I'd look at the class and I say, well, what exponent turns everything into 1 except the number 0? What exponent turns everything into 1? And everybody tells me 0. So it's still the same idea. And lastly, exponent needed to turn 5 into 5. And that's kind of a weird thing to say. 5 is already 5, but remember, an exponent, if it's not written, is understood to be 1. And so this is 1. Did these last two? Because these last two start us into properties of exponents. We'll be spending quite a lot of time talking about properties of exponents. Or excuse me, properties of logarithms. These last two take us into properties of logarithms. And we'll be spending a lot of time talking about properties of logarithms because logarithms are just exponents, and exponents had a bunch of rules and properties. So because exponents have rules and properties, and because logarithms are just a specialized exponent, here we are, they were just specialized exponents. Because there's properties of exponents, there's going to be properties of logarithms. And these last two give us our first two properties. Namely, right here, basic logarithmic properties, log base b of b is 1, and log base b of 1 is 0. So this is telling me that if the base and the argument are the same, the answer is always 1. And that's what we saw. Let's get these last two ones, we can see them all. That's what this last guy said. The exponent needed to turn 5 into 5. This would be the exponent needed to turn b into b. It's always going to be 1. And then the log of 1 is always 0 because 0 turns every number, 0 as an exponent, turns every base into 1 with the exception of 0. We're never going to talk about 0 over 0. So when I say that the exponent of 0 turns everything to 1, I am excluding the number 0. 0 to the 0, we're never going to talk about. So here are first two properties. Okay, what else are we going to do with logarithms? So here I did a little table of values here. We're going to look at the function log base 2 of x, or y equal log base 2 of x. And I just did a little table of values here. And I don't want to go too much into this table of values, but again, it was just about finding exponents, and I don't want to get way into it. So if you want to come see me and say, oh, really, explain this table to me in great detail, come see me and I'll explain this table in great detail to you. But I made a little table here, and so just go with here's my x coordinate, here's my y coordinate, x, y, x, y, x, y, x, y, x, y. And here's this little checking thing. Don't worry about it too much. There's my logarithm graph. That's what I care about. There's a basic log graph. Note my basic log graph and all basic log graphs. So we're talking log base some number of x. Basic log graphs. They're all going to go through the point 0, 1. All of them are going to, or excuse me, that's the point 1, 0. They're all going to go to the point 1, 0 because of this fact right here, that log of 1 is always 0. So there's my basic log shape. Basic log shape. And we can see from this basic log shape that the domain is 0 to infinity. Notice parentheses at the 0, that it's coming very, very close to the y-axis here, which is x equals 0, but it's not touching. So that's what's happening here, that this comes close to x equals 0, but does not touch. And over here, this is going up and right forever. It's going really slowly up, and if we graphed it out a long, long way, it would look almost exclusively horizontal, but it's not really going horizontal. It's going very slowly up and right forever. So the domain, left to right, 0 to infinity, which means we can only find the domain of positive numbers. And we mentioned that before when we first put this up there and I said the argument can only be positive. That corresponds to the domain, that we are only doing logarithms of strictly positive numbers. We can only find log base 2 in any sort of logs of strictly positive numbers. It can be also seen that the range is negative infinity to infinity, low to high. It's going down forever and up forever, so negative infinity to infinity. And lastly, we can see that there's a vertical asymptote at x equals 0. And so again, the point here is going to be that that's the basic log shape of all basic logarithms. Log base 2, log base 22, log base whatever. Going to have that same basic shape. So using that, we'll do a little transformation graphing here. Use transformations of f of x equal log base 2 of x to graph the given function. Find the graph's vertical asymptote, domain, and range. So again, my basic shape looks something like that, where it goes through that point 0, 1. So h of x equals 5 plus log base 2 of x plus 2, which I could rewrite to this way. Just putting that 5 on the end where we're more used to seeing it. So the plus 5 is going to send me up 5 units. The plus 2 inside that logarithm, horizontal, opposite to what you expect, left 2 units. So I'm going to move that point, that 0, 1 point around. So I'm going to start with that guy. I'm going to move it. So we're going to move that guy up 5 units. 1, 2, 3, 4, 5, and left 2. So that's where that point is going to be. I guess we'll go ahead and draw it in blue. Now, the vertical asymptote. I want to move the vertical asymptote. So moving this vertical asymptote. So we're moving this guy right here, moving it 2. 1. I just lost my train of thought. Sorry about that. I didn't move this far enough. That's fine. So let's pretend this didn't happen. That's what's wrong. Moving this 2. So 1, 2. So it's going to go over 2, up 5. And I really should have just done this in blue. It would have been better. So up 5, over 2. I really shouldn't be so lazy. I should just redo this whole video, but I don't want to. So over 2, up 5, that's where that point is going to be. So I took this point here, moved it the wrong direction. Wow, I really should start this again, shouldn't I? But we're not. You can just watch me fumble through it. This way you know I'm not perfect. Left 2, 1, 2, right there. 1, 2, up 5. That's where that point is going to be. Then, moving the asymptote over 2. So here's my asymptote right there. There's my asymptote. Move that 2. 1, 2. And so there's my asymptote right there. And then draw that same basic shape. And there's the graph. So there I finally got the graph, doing everything right, taking that point, moving it left 2, 1, 2, up 5 right there, and then moving that asymptote, left 2, right 5. End of video.